Good afternoon, everyone. My name is Aidar, and I'm representing today TriboNet team. Welcome, and thank you very much for being with us. Today's seminar is part of our monthly seminar series that we have launched since summer of this year, with the goal of promoting the knowledge in tribology field, but also tribology itself. I would like to thank our sponsor and co-organizer of today's seminar, Optimal Instruments. Optimal Instruments specializes in manufacturing equipment for tribe testing and solving tribological challenges. Today I'm pleased to announce that we have with us Dr. Mathias Woydt, and the topic for the seminar is the tribological challenges and their solutions to electrified powertrains, which is a very interesting topic, of course. Now, before we start, a quick plan for today. We will have a around 30 minutes presentation followed by a Q&A session. We have quite some participants today, so during the presentation you won't be able to ask questions, but you will be able to chat, and we can address the questions after the presentation. And I will do a short introduction of Dr. Mathias Woydt, for those who doesn't know him yet. Dr. Mathias Woydt studied and received his PhD from the University of Berlin, Berlin University of Technology, I'm sorry. Currently he is managing partner of Matri-Lub, Germany, and vice president of the German Society for Tribology. He is the recipient of the ASTM Award of Excellence and STLE Fellow. Dr. Woydt has more than 51 authored patent applications. He has more than 380 reviewed industrial and scientific papers, published in German, English, and French. The publications generated more than 2,900 citations. Now, he is a lecturer at the Technical University of Berlin for Tribology. He was 33 years as the head of Division of Tribology Wear Protection with BAM Federal Institute for Materials Research and Testing in Berlin. Without further ado, Matthias, the floor is yours.
Okay, I appreciate your kind introduction. Ladies and gentlemen, it's my great pleasure to talk to you about some hidden aspects of tribology or tribology testing, especially for electrical vehicles or electrified powertrain. The point is we have lubricants, and the lubricants normally they must meet frictional properties, wear or longevity, in some cases fretting, oxidation, a lot of properties what we will know. We have test methods, we have big experience, and now we have for electrified systems a lot of new properties or demands which come on top. We have the issue of heat transfer, thermal conductivity, and heat capacity. We have much more materials involved, so the issue of material compatibility and the question if the corrosion inhibitors matches well with electrical circuits, and also the electrical properties of the lubricant itself, which can generate insulation or earthing, are properties and demands which come on top. And additional, in the far future, there may also come issues like biodegradability or the content of renewable contents. So the two key applications today which we can call electrified are the wind turbines and the drivetrains in vehicles. The dilemma is that we have very fast put into the market products for which we do not have clear, dedicated test methods. On the left side, of course, there exists a lot of test methods at ASTM, DIN, IEC, but these were developed for for fire-resistant fluids or for heat transfer fluids, but not for greases or for lubricants itself. The only new test method we have now is the DIN draft 51111, which is clearly dedicated from the test setup to oils and also greases. So the problem is that we have, let's say, not dedicated test methods so far. The existing ones were developed for transformer oils, fuels, and fire-resistant fluids, and all must now be adapted to the specific applications of electric vehicles and electrified powertrains, and for fluids, oils, and greases. What you observed, or what one observes today in electrified system, is you can have a lot of different types of currents: induced shaft voltages, parasitic capacitances, EDM, tribocharging, rotor earth faults, or circulating currents. And the consequence for the tribo systems itself are arcing pits in the raceway, washboard-like ridges on the bearing surfaces, and oxidation of loops by arcs and arcing. This is a new demand which is composed into two working areas. First, the electrical properties of the fluid, of the lubricant or the grease itself, and later on, what is so far not taken into consideration, what will happen in the tribo system itself. So what you see here on the left side is, for instance, for two greases as function of temperatures, the impedance as function of frequency, and you see by one shot that you have here two greases which differ significantly in their impedance properties by orders of magnitude, and the levels depends from the temperature. This already shows that you have to test and you have to map at least at different temperatures. If we look in a ball bearing, which is a typical tribo element in an electrified system, you have, of course, the electrical properties of the bulk material, but what was forgotten is what happens in the tribo-film, because we need tribo-film to reduce friction, to protect against wear, and especially against scuffing. And now the questions comes up, what kind of tribo-film is now good, and a conductive one or a non-conductive one? And this is a challenge for today. Basically, what happened on a surface is shown here. On the right bottom, you see that tribo-films are formed on the microasperities first. They are not so thick. They have 50, 100, 200 nanometers in thickness. And if we use zinc compounds, they are mainly composed by iron oxides and zinc polyphosphates. And on top, other additives can absorb. The consequence, so this problem is not new. You see here old work from Klüber. You have on the left side the coefficient of friction for different additive packages, and on the right side you see the electrical contact resistance for those additive packages, and you see you have a mismatch. The electrical contact resistance has per se nothing to do with the frictional properties, the anti-wear properties, or the extreme pressure properties. That's why we have to look in the future also on what happens in the tribo contact itself. On the right side, you see a new test method developed by Optimal Instruments for the SRV. You can determine the friction under rolling motion, and Here you have two different greases, and you see how the evolution of the contact resistance is different for these two types of oil, which differ first in the base oil type and second also in the additive packages. And we will see in the following what will be the tribological consequences. Let's start with threading. You see for these two greases, the electrical contact resistance measured at 50, 80 and 120 centigrade according to ASTM D7594. Even ASTM 7594 not includes the electrical contact resistance, but you see here the evolution of the electrical contact resistance. And here is clear that the tribo-film has, over temperatures, in both cases, completely different electrical properties. And now, depending from your application, you can be on the good side or on the war side. And especially here, you see that at 50 centigrade, you have a quite high contact resistance for grease number 1. And the opposite is for grease 2, where you have at 120 centigrade a high contact resistance. This example already shows here that if you want to select lubricants or greases, you must decide what you want, a low or high electrical contact resistance, and this contact resistance should be independent from the temperature, at least in the range of operating temperatures of your application. Another point is it's the same test, but you see now how it looks like the wear scars. If you look to grease 1 at 80 centigrade, even at all temperatures, this grease matched the requirement for NLGI HPM HL spec. You see at 80 centigrade there is a beginning pitting, and the same for the grease 2 at room temperature, which decreases as trend with increasing temperature. So not only the evolution of the contact resistance should be regarded, but also the morphology of the wear scars. And to make it now a little bit more complex, you see here for the greases the coefficient of friction and the evolution of the electrical contact resistance. Friction is in this diagram on the left side, and the electrical contact resistance is on the right side. And what you see clearly, friction and electrical contact resistance have no correlation and nothing to do with each other. So if you only look on the evolution of the coefficient of friction, you lose any information regarding the electrical properties of the tribo-film. Here you see on the right side that both greases differ significantly in their electrical properties, especially the electrical contact resistance of the bulk grease, the electrical conductivity, permittivity, and also the dielectric loss factor. And on the tribology in the middle, you see both from the tribological point of view, you would say both have the same frictional behavior, both have the same 4-ball load, but on the left side you see the associated electrical contact resistance. There are significant differences over temperature and also between these two greases. If we look now in the load step test, according to ASTM 5706, where you record what you see on the left side, you record the OK load, which is the step function you see. Every 2 minutes you increase the load by 100 Newton, and in parallel the electrical contact resistance, and on the right side you see until scuffing the evolution of the coefficient of friction, and also clearly here is the evolution of the coefficient of friction has nothing to do with the evolution of the electrical contact resistance of the tribo-film. And for both cases, it is the same. And here you must also have, in an ideal case, products where the properties of the contact resistance is independent from the ambient temperature. Here you see it in comparison between the friction and wear test according to ASTM 5707 in comparison to the EP test. So both greases respond to temperature in a different way, and both greases have a significant differences in the evolution of the electrical contact resistance and also in the level. But from the tribological point of view, they don't differ. Okay, another point is the electrical motor itself, because I think not only for the battery itself and the inverter and also the motor, there is a need to have a wet solution, which means that also the motor is cooled, and a trend is going to hairpins, not only to have coils. And what you see on the left top of those hairpins, they are laser welded at the end, but this region has no lacquer. So the question comes up how to additivate the fluid. But as you see, you have a lot of blades which by vibrations coming from the road or from magnetic fields will have a microslip. And those lacquer here are polyimide ester, and the second coat was polyamide imide. They have 120, 150 micrometer in thickness, but over time they have micro movements, and at the end of the day, the risk is that this micro movement will wear off the lacquer, the coating, and we all know that polymers are sensitive to lubricants. That's why for gear oils, hydraulic oils, for engine oils, you have a lot of static compatibility tests of polymer with a lubricant or a fluid. But here in this case, you have on top tribological solicitation, and the question is what will happen in this case. To mimic it, you see on the right side that you take just such a hairpin and you use a roller, and the roller is inclined by 10 degrees according to DIN 51834 part 4 or ASTM D8316, and you make a fretting movement. So what can happen? You see here how the wear tracks on the pin looks like. If we start on top, you have mild wear, followed by medium wear, or you have a fully plastic flow. And on the top, you see a beginning brittleness that these lacquer by the combined solicitation of fluid and tribology gets brittle and a delamination start. This is not desirable in an application because you have on the long run the risk that you get short circuit and your motor loses power. So if you look now to the results, you see on the left side a dry case, coefficient of friction, left side of the diagram, electrical contact resistance on the right. And at the beginning of the test, clearly the lacquer is insulating, but at a certain point you see a drop in the electrical contact resistance, but the friction is uninfluenced by this. Again, also here, you see that the friction alone is no indication for systems which are used in EVs or electrified systems, powertrains. On the right side, you see a fluid, and you have an evolution of the coefficient of friction, and where the drop of the electrical contact resistance happens, which means that the coating is fully worn, the friction is unaffected. So this is again not an indication. If we take another fluid, you see that the contact resistance begins to weaken, but the friction is unaffected. And these different observations matches with the morphologies of the wear tracks shown before, because already the static interaction of a fluid or additive from a fluid with a polymer are completely different. There can be some protection, there can be brittleness which is engaged, or the polymer can also soften, and then you see here different evolutions in the friction associated with the electrical contact resistance. This means if you develop fluids, lubricants or greases for EVs or electrified powertrain, you must imperatively combine the friction signal with the electrical contact resistance, and for sure in the future you have to put on top the voltage, because all those circuits have a voltage of 400 or 800 volt, and this will accelerate, and this will make the test much more severe. So finally, it is clear that the different electrical properties of lubricants represent additional technical requirements for which dedicated test methods must be developed, where we have today so far a lack. Besides the bulk electrical properties of lubricants, electrical properties of the resulting tribo-films are also of great importance, what the people or many so far not have seen or perceived. The electrical properties of the tribo-film shall be invariant with the range of operating temperature in the respective application, which means you must map over temperature and you cannot rely on only one temperature. A static compatibility test of plastics are well known, but the superimposition with tribological solicitations increases severity, especially in the case of hairpins or at any other sections where you have fretting due to vibrations coming from the road or from magnetic fields. The tribometric test must be combined with electrical contact resistance. This is absolutely clear, and there's no way around. Besides the bulk electrical properties of lubricants, the retention of the electrical resistance under fretting of the coating is of great importance. So in the future, we will not only look that the friction and wear properties are retained over the usage time or over drain, but the same requirement will also be needed to follow for the electrical properties of the bulk lubricants and also of the tribo-films, and this will make the development much more complicated. But at the end of the day, we have the tribometric solution to combine electrical properties in a tribo test with the friction and wear properties. So I am here at the end, and we have now some time for questions and answers.
Thank you, Matthias, for a great presentation, and for the audience in the chat, please raise your hand or write a question in the chat, and we will unmute you so that you can ask a question. Before people are typing the questions, maybe I'll start with the question. So you can do you can do the electrical resistance measurements with the tester that you used. And I'm wondering if you could also induce charge damage during the test. So basically, can you put electric field to the sample?
No, but the next steps are, as mentioned, to have a voltage and also to simulate arcing by having a defined current going through the tribo contact, because arcing is energy, and a tribo-film or the formation of a tribo-film will also react on that. Plus, you have to look if your tribo-film is conductive or non-conductive. So these will be two additional options for the future, having a voltage on top and be able to send a current, a defined current through the tribo contact.
Yeah. Yes, thank you. Thank you for the answer.
Either, I guess we have a question from Claudia. You can unmute.
Claudio, you can unmute yourself and ask the question.
Claudia, could you please unmute yourself and ask the question?
Well, maybe before Claudio asks, so there is another question from
Ravi Kiran.
Ravi Kiran. How do you see graphene-based lubricants as an alternative to the conventional lubricants?
This is a solution 25 years ago the Japanese car makers have introduced in their bearings, where you have a monobelt going through all accessories. But there are other options to increase the conductivity. But as said, you not only have to look on the conductivity of the bulk lubricant, but also of the tribo-film. And if now the graphite will go into the tribo-film, maybe not. But graphite is a proven option to increase electrical conductivity. And it's not new. It was, as said, done in Japan in the mid of 90s.
Thank you. And there's another question. Have you tested grease with different friction modifier fillers?
Yes, I know. You must see Optimal Instruments is not a formulator, yeah. But in the frame of services, Optimal Instruments offers, and those systematic studies were purchased by additive suppliers, and you see significant differences that some additives which are a good friction modifier under the conditions of an electrified powertrain may generate insulating films at specific temperatures.
Yeah, thank you. There's another question from Quentin. Is tribo corrosion a big concern for electrified powertrain applications?
Tribo corrosion is more arcing for the oxidation stability. Tribo corrosion is a problem. Tribo corrosion not so much, but the corrosion issue for the whole circuit, because you have much more materials, different types of materials involved than in a normal engine or in a gear. This is an issue, and now the question is how you can find a multi-material protecting anti-corrosion additive which not interferes with pins if you may have microelectronics.
Thank you.
The consequence is really that the formulation will change and have to change due to the criteria of electrical systems.
Thank you. There's another question.
Manash, but maybe we can actually unmute people so that they can ask this out actually. So,
yeah.
Claudio,
you can unmute.
Yeah, you can unmute and ask your question. Or at least say thank you, or the question is answered. Okay.
Or you can unmute Narsimulu.
Yeah. Okay. Thank you, sir, for the nice sharing. It's very interesting to see always in this electrical equipment how exactly tribology plays a part. So here, since you touched upon fretting, I have worked on linear bearings, fretting issues and other. So to avoid the fretting, how is this clamping force, okay, on the laminates that you showed, those parallel plates, like you are right, like very small motions because of the force fluctuations it is tending going to have. So many factors will play a part, like including surface roughness of it, what kind of clamping force, how exactly it's going to be, how is it being modified, and also have you studied the wear debris from it?
No, we didn't study the wear debris. We have, and we will show this in 10 days. That if you reduce the contact, if you reduce the normal force, and if you reduce the contact stress, you increase the lifetime, but basically you not change so much the problem of fretting and of the wear of the insulating lacquer or insulating coatings. And there are some, let's say, returns from the field where the people claim or found a loss of power, and it is clear if you have a short circuit between the different pins, you have less wirings which are active, and then you have a loss of power. So this is a point to optimize the material, that the material is better resistance against the fluid use and also the fluid itself. Okay. Yeah. And as said at the beginning, we have a lot of additional requirements for those fluids, which are at a certain extent contradictory to the past tribological experience, and this will need to new formulation, and also suddenly other additives and base oil will come onto the top priority.
Mm. Yeah,
but there will be a solution. I'm absolutely sure that formulations will be found. Yeah.
Just a quick one. In my experience with the linear bearings, the rollers sometimes both have slip and rolling. So that slip gives rise to the creeping one and starts crawling out. So there I observed the surface roughness plays a part. So here again, like how is this RA value of the surface roughness as compared to the film thickness? So that we know what type of tribological condition exists there.
Yeah, but as you know, all ball bearings, they have very smooth, super polished surfaces, and the tribo-films are in the range of RA. Yeah, right. They can have 100 or 150 nanometers, but most of those are much smaller, 40, 50, 60. But it may that now, due to arsing and due to other compositions in such functionalized fluids for EVs and electrified powertrains, we will have a little bit higher tribo-films. But this is, I think, not a big problem for the application. The biggest problem is to have a tribo-film which is independent in its electrical properties from all operating temperatures, you may face in the application. Otherwise, you will have customers that have troubles and customers that have not troubles. This is more a problem for the OEM at the end of the day, but this problem will be reverted to the formulator to have a formulation where the electrical properties are invariant to oil temperature.
Yeah. Thank you.
Next question,
Hello.
Rory.
Yes. Thank you for giving me the floor. What is the breakdown voltage requirement for tribo-fluids?
Oh, hi. Sorry, who's
I don't know.
asking the question?
Because this has nothing to do with the breakdown voltage here. The breakdown voltage is not my study here, what I have shown today. I focus on the tribo-film itself. What happened on the tribological stressed surfaces. It has nothing to do with a requirement on breakdown voltage. Yeah?
Okay, thank you.
Hi, good afternoon. It's Rory Taylor here. I asked a question about washboarding.
Yes.
And whether you had any thoughts on the mechanism for generating washboarding, and whether conductive tribo-films would eliminate washboarding or may improve it, or if you think it's more of a dynamic problem which the tests that you've carried out might not resolve.
No, it's very complex as white etchings, where you have different philosophies and understandings behind. Honestly, it's too early. I have a personal opinion on the electrical properties of a tribo-film, but let's say this is my personal knowledge. Yeah.
Yeah, are you willing to share that personal knowledge?
No.
Might be quite interesting. No.
Not for free.
Okay.
Yeah, but it's the question of electrostatic issues. You can also try to solve this by design. Yeah, you can try to solve this with silicon nitride or with zirconia rolling elements by brushes. There are many solutions to minimize the problem, but still you have the issue of the tribo contact itself. Yeah. There is this, I can tell you, if you use silicon nitride or some films, they have the capability to store inside charges. It is called electret. Yeah, this property, and at a certain point, it can suddenly go out from the surface. So it will require some more testing. That's why also we have not only the electrical contact resistance. There are so many other electrical properties you have to include in this game. Yeah, and the DIN 51111 addresses all those different electrical properties.
Okay, no, thank you very much. Thanks for the presentation and the response.
Thank you. I think we have last question from Claudio. It seems, I'm then reading the question. It seems that 800 volts to 1000 volts will be the new standard. How will it affect the test results?
It will increase the severity. If you imagine you make those tests and you wear down the lacquer, then you reach much earlier the point where you have an arc. To see the impact of lubricant on the fretting behavior, I think you not consequently need to put on top a voltage, but for the friction, for the normal friction and wear test related to bearings, it's a different case. Yeah. But basically, you can add in this test also a voltage, and then you will certainly shorten the test time. But they are not so long here. On the other hand, if you go down to 50 megapascal, you have a lifetime of the film in the range here of 3 days under these 50 Hertz conditions. And if you put a voltage on top, you reduce it to 1 day. Yeah. But I think these test conditions here are quite fair. Also from the testing time, you see if you have tested a lot of fluids, significant differences in this time. And also if you take a base oil plus one additive, base oil plus the other additive, and then you see that some additives which are perfect for normal tribological operation may have here not adverse effects, but are not on the top in the ranking.
Thank you. I hope that answers all the questions from Claudio. I think we don't have more questions. So yeah, I think Claudio says thank you. So yeah, if there are no further questions, then we can close our today's session. But before we close, I just wanted to let everyone know that the recording of the seminar will be available on our website, and the link will be sent via an email. If you have further questions, then I think it's best that you can contact Dr. Woydt directly, or you can also, of course, go to TriboNet and write the question there. Our next seminar is planned for in January with Professor Ashley Martini as a speaker, so stay tuned. And I hope you guys enjoyed this seminar as much as I did. And I would like to thank Dr. Woydt again for a nice presentation, for the wonderful discussion. Thank you all for the questions, and I wish you all a good evening, day, and weekend. Thank you very much.
Thank you. Thank you all.